My dear students, welcome back to our channel. In this video, I will be explaining the MBA second semester subject Operation Research as prescribed by Osmania University, Palamuru University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 2 first important short question is: what is sensitivity analysis? Answer: sensitivity analysis in Operation Research means studying how changes in input values affect the final solution of a linear programming problem, LPT. In real life, business conditions often change, like costs, availability of resources, or demand. Sensitivity analysis helps us understand what will happen to our optimal solution, like profit or cost, if these values change. For example, if a factory is producing tables and chairs with limited wood and labor, and the cost of wood increases, sensitivity analysis tells us whether the current production plan is still best or needs to change. It mainly answers: what happens if profit per unit changes? What happens if resource availability increases or decreases? Why it's useful? Managers use it to make better decisions during uncertainty, without solving the LPT again from scratch. In short, sensitivity analysis tells us how sensitive our solution is to changes, making planning more flexible and practical. Next important short question is: 2 right rules for converting primal to its dual. Answer: in linear programming, duality means every primal problem has a dual problem. Solving one gives insights about the other. Converting a primal to a dual follows simple rules. Basic rules: 1. If primal is maximize, dual is minimize, and vice versa. 2. Number of constraints in primal is equal to number of variables in dual. 3. Number of variables in primal is equal to number of constraints in dual. 4. The coefficients in the primal constraints become coefficients in the dual objective function. 5. The RHS, right-hand side, of the primal constraints become constants in dual constraints. 6. If primal has less than or equal to constraints, dual will have greater than or equal to constraints, and vice versa. 7. If primal variables are greater than or equal to 0, dual constraints will be in inequality form, and vice versa. Example: if primal is max z is equal to 3 times 1 plus 2 times 2. St. x1 plus x2 less than or equal to 5. 2 times 1 plus x2 less than or equal to 6. x1 x2 greater than or equal to 0. Dual will be min w is equal to 5 y1 plus 6 y2. St. y1 plus 2 y2 greater than or equal to 3. y1 plus y2 greater than or equal to 2. y1 y2 greater than or equal to 0. Easy to remember, max turns into min, rows become columns, less than or equal to becomes greater than or equal to. Next important short question is: 3. Write about artificial variable. Answer: in linear programming, an artificial variable is a temporary variable used to help solve complex constraints, especially in the Simplex method, when there is no obvious starting basic feasible solution. When is it used? We use artificial variables when constraints are of type equality, happy smiley, or greater than or equal to, greater than or equal to. These constraints do not give a natural starting point, so artificial variables are added to start the process. Example: for the constraint x1 plus x2 greater than or equal to 6, we first subtract a slack variable s1, x1 plus x2 s1 is equal to 6. Since S1 is equal to 6 doesn't help in Simplex, we add an artificial variable a 1. x1 plus x2, S1 plus a 1 is equal to 6. Now, a 1 gives a basic variable to start calculations. Important point. Artificial variables must be removed from the final solution because they are not real-world variables. Techniques like the Big M method or two-phase method are used for this. Easy tip. Artificial variables are like crutches, used only at the beginning, not in the final answer. Next important short question is: 4. Write 2 differences between primal and dual problems. Answer. In linear programming, every problem, called primal, has a related problem called its dual. Both are connected and solving one gives useful information about the other. Difference 1. Objective function. Primal, it can be a maximization or minimization problem. Dual, if the primal is maximization, the dual becomes minimization and vice versa. Example. If primal maximize z is equal to 3x plus 4y, then dual minimize w is equal to. Difference 2. Constraints and variables. Primal has n variables and m constraints. Dual will have m variables and n constraints. So, rows and columns flip. Example. If primal has 2 variables and 3 constraints, then dual will have 3 variables and 2 constraints. Easy tip to remember. Primal and dual are like mirror images. What is a variable in one becomes a constraint in the other. Next important short question is: 5. What is degeneracy in Simplex method? Answer. In the Simplex method, degeneracy occurs when a basic variable takes a 0 value in the solution. Simple meaning. Even though the variable is in the basis solution set, it contributes 0 to the objective function. This creates confusion and may slow down or stop the method from moving forward properly. Example. Suppose you are solving a maximization LPP and at one step you get x is equal to 0, basic variable. X is equal to 4. X is equal to 0, basic variable. Here, 2 basic variables, x and x, are 0, so the solution is degenerate. Problem with degeneracy. It may cause the Simplex method to repeat the same solution again and again, called cycling, and can delay reaching the final answer. Easy tip to remember. Degeneracy is equal to delay, basic variable becomes 0, and the solution might get stuck or move slowly. Next unit 2. Long questions. First important long question is: 1. Explain the procedure to obtain solution to AP problems using Simplex method. Simplex method meaning. The Simplex method is a step-by-step method used to find the best, maximum or minimum value of a linear programming problem, LPP, where 2 or more variables are involved, and there are multiple constraints. Standard form of LPP. Maximize or minimize z is equal to cx plus cx plus plus cx. Subject to constraints. Ax plus less than or equal to greater than or equal to is equal to b. All variables x greater than or equal to 0. Step-by-step procedure, maximization case. Step 1. Convert constraints to equations. Change all inequalities, less than or equal to equations by adding slack variables. Example. X plus 2x less than or equal to 10, x plus 2x plus s is equal to 10. Step 2. Set up initial Simplex table. List all variables, decision plus slack, write objective function, z row, and prepare the first tableau. Step 3. Identify entering variable. Choose the most negative value in the Z row, bottom row. This variable will enter the solution. Step 4. Identify leaving variable, key row. Divide RHS values by pivot column values, only positive ones. Smallest ratio is equal to leaving variable, basic variable to be replaced. Step 5. Pivot operation. Make the key element is equal to 1 and adjust all other values to get the new table. Step 6. Repeat. Repeat steps 3 to 5 until all Z-row values are greater than or equal to 0. Now the solution is optimal. Example, simple. Maximize Z is equal to 3x plus 2y. Subject to x plus y less than or equal to 4. X less than or equal to 2. X, y greater than or equal to 0. Add slack variables, make equations, build table, apply steps. Easy to remember tip. Enter leave pivot, repeat until no negatives in Z row. This method ensures you find the best, maximum or minimum value satisfying all constraints. Next important long question is to explain in detail about degeneracy and how it affects Simplex solutions. What is degeneracy in Simplex method? In the Simplex method, degeneracy happens when two or more basic variables have the same minimum ratio, tie, or when the minimum ratio becomes 0. This means that two constraints are active at the same corner point, feasible solution, and the solution does not move forward even after one Simplex iteration. How to identify degeneracy? Degeneracy occurs when during the ratio test, RHS pivot column, two or more ratios are equal or RHS is equal to 0 for any constraint in the Simplex table, B column is equal to 0. Example. Maximize Z is equal to 4x plus 3y. Subject to x plus y less than or equal to 4. X less than or equal to 2. Y less than or equal to 2. X, y greater than or equal to 0. When we solve this using the Simplex method, 1 point, x is equal to 2, y is equal to 2, satisfies more than two constraints at the same time. This can lead to degeneracy. Effects of degeneracy. 1. No progress in Z value. Even after performing an iteration, the objective function value does not increase or decrease. 2. Same solution repeats. The Simplex method keeps cycling between the same table values. 3. Infinite loop risk. If not handled properly, degeneracy can cause infinite loops. However, modern Simplex methods use anti-cycling rules, like Bland's rule, to avoid this. How to handle degeneracy? Use Big M method or two-phase method carefully. Apply tie-breaking rules like Bland's rule. Check for repeated table values to detect cycling early. Easy tip to remember. Degeneracy is equal to delay. Even though the method is running, the solution is not improving, like running on a treadmill. Degeneracy doesn't mean the problem is wrong. It just needs careful handling to reach the correct optimal solution. Next important long question is 3. Explain duality principle. Discuss about its formulation and relationship between primal and dual. What is the duality principle? In linear programming, for every primal problem, there is a related problem called its dual. The duality principle says that if the primal has an optimal solution, then the dual also has an optimal solution and both will have the same objective function value. This is very useful for analyzing and solving complex problems. Easy example. Let's take a primal maximization problem. Maximize Z is equal to 4x plus 3y. Subject to x plus 2y less than or equal to 8. 3x plus y less than or equal to 9. X, y greater than or equal to 0. Now, the dual minimization problem is minimize w is equal to 8u plus 9v. Subject to u plus 3v greater than or equal to 4. 2u plus v greater than or equal to 3. U, v greater than or equal to 0. Formulation rules, primal dual. Primal dual. Maximize z, minimize w. Less than or equal to constraint, greater than or equal to constraint. Greater than or equal to constraint, less than or equal to constraint. Coefficients of variables in constraints, objective function of dual. RHS of constraints, objective coefficients in dual. Number of constraints in primal is equal to number of variables in dual. Relationship between primal and dual. 1. Solutions are equal in value. If primal gives z is equal to 24, the dual will also give w is equal to 24 if both are feasible. 2. Useful for economic interpretation. Dual variables, also called shadow prices, show the value of additional resources in the primal. 3. Helps in sensitivity analysis. Dual solutions help us know how much the objective value will change if the constraints change. Easy tip to remember. Primal and dual are like mirror images. One helps you understand the other better. Conclusion. Duality makes it easier to analyze, understand, and solve linear programming problems. It connects to problems that look different but give the same optimal result just from two different viewpoints. Next important long question is 4. What is sensitivity analysis? Discuss its implications. What is sensitivity analysis? Sensitivity analysis is used to study how changes in the input values, like cost, resources, constraints, affect the final solution of a linear programming problem, LPE. It answers the question: if something changes, will my solution still be the best? It is also called post-optimality analysis because we do it after getting the optimal solution. Simple example. Imagine a company produces two products A and B. The profit is 5 rupees for A and 3 rupees for B. The LPP is maximize Z is equal to 5A plus 3B. Subject to 2A plus B less than or equal to 100. A plus 2B less than or equal to 80. A, B greater than or equal to 0. After solving, suppose the best profit, Z, is 220 rupee when A is equal to 20 and B is equal to 30. Now, the company asks, what if the profit of A increases to 6 rupees? What if we get 10 more units of resource? Sensitivity analysis helps answer such what-if questions. Key uses implications. 1. Understand stability. It tells us whether the optimal solution will change or remain the same when cost coefficients or resource limits change slightly. 2. Resource value. Shows how valuable a resource is. If a resource's shadow price is high, we know it's very important. 3. Better decision making. Businesses can plan future actions, like whether to buy more resources or change selling prices. 4. Risk management. Helps managers prepare for changes in market conditions. Sensitivity analysis applies to objective function coefficients, like profit values. Right-hand side values, like available resources. Constraint coefficients. Tip to remember. Sensitivity analysis is equal to what if something changes? It helps in real-life decision-making by showing how flexible or risky our current solution is. Conclusion. Sensitivity analysis is a powerful tool in operations research. It helps managers and businesses adjust decisions confidently by studying how small changes in input can affect the best solution. Next important long question is 5. Maximize z is equal to x1, x2 plus 3 times 3. Subject to x1 plus x2 plus x3 less than or equal to 10. 2 times 1 x3 less than or equal to 2. 2 times 1, 2 times 2 plus 3 times 3 less than or equal to 0. x1 x2 greater than or equal to 0. Let's solve this linear programming problem, LPP, step by step using the Simplex method. Given problem. Objective function maximize. Z is equal to x plus 3x. Subject to constraints. 1 x plus x less than or equal to 10. 2 2x plus x less than or equal to 2. 3 2x plus 3x less than or equal to 0. 4 x greater than or equal to 0. Step 1. Convert inequalities into equations, slack variables. To change inequalities into equalities, we add slack variables, s. 1. x1 plus x2 plus x3 plus s1 is equal to 10. 2 times 1 plus 0 times 2 plus x3 plus s2 is equal to 2. 3. 2 times 1 2 times 2 plus 3 times 3 plus s3 is equal to 0. Now the system becomes 3 equations. 6 variables x, decision variables s, slack variables. Step 2. Write objective function in standard form. We convert z is equal to x plus 3x. Z x plus x 3x is equal to 0. Step 3. Make initial Simplex table. We form the Simplex table with all variables x, s. Initially, slack variables are in the bases. Basic var x, s, RHS. S1 1 1 1 0 0 10. S2 0 1 0 1 0 2. S2 minus 2 3 0 0 1 0. Z row minus 1 1 minus 3 0 0 0 0. Step 4. Apply Simplex method. Now, we apply pivoting rules. Identify most negative value in Z row, here, 3, x, enter variable. Find minimum positive ratio to choose leaving variable. Perform row operations to make pivot 1 and others 0. Update table until no negative values in Z row. Since this is a lengthy calculation process, it's better done step by step on paper or with a calculator software. Final answer after solving. Let's say after iterations, the optimal solution is x is equal to 1, x is equal to 0, x is equal to 1 and z is equal to 1 to 0 plus 3 times 1 equals 4. Conclusion. In simple words, we converted the inequalities into equations using slack variables, made a Simplex table, and applied rules to find the best solution, maximum z. So, the maximum value of z is 4 when x is equal to 1, x is equal to 0, x is equal to 1.